Hello everyone. In this video, I'm going to present joint work I did with Eduardo, Mateus, and Dario. My name is Renato. And this work is called An Argument in Favor of Strong Scaling for Deep Neural Networks with Small Datasets. And in this work is going to be presented in HPML 2018. The website is hpml2018.github.io. Be sure to visit it. There's lots of papers, really interesting papers there. So please visit the site. Okay, so this work is positioned in the intersection between deep learning and some parallel implementations, which is completely aligned with the theme of HPML, which is high-performance computing and machine learning. And the key takeaway of this presentation is that a strong scaling approach can both be faster than weak scaling alternatives and reliably converge to a solution, which may not be the case with weak scaling alternatives. So this is the gist of it. Let's see what do we mean by that. But first of all, why are we doing this? Well, it turns out that we saw that in recent years there have been many works, many papers focusing on ever-growing models in big data sets. The most notorious example is ImageNet, which is a 14 million sample data set. And well, everyone seems to be doing it and training state-of-the-art models with it. And what they are doing is they are essentially increasing the batch sizes so that training can proceed in a smooth way and faster. So one example is this paper by Facebook, Accurate Large Mini-Batch SGD, Training ImageNet in 1 hour. This is actually a quite interesting paper. Another is scaling SGD batch size to 32K for ImageNet training, again with big batch sizes. Power AI DDL by IBM Research as well is using large datasets to large batch sizes to train large models, and this work is interesting as well. Don't decay the learning rate, increase the batch size. Well, these are all really good papers. I'm not criticizing them. And they use relatively large data sets. Even the smallest one is CFAR, but CFAR has 60,000 samples. It can be bigger than some other data sets we have around. But that shouldn't be a problem since we live in the big data world, right? Data is abundant. Well, okay, it does make sense to study large models. It has interesting challenges. It has greater appeal because everyone wants to work with big machines. Who doesn't? And especially this is good marketing when cloud providers and big technology providers actually are able to show and demonstrate expertise in devising and training models fast. This is actually quite good. But some questions arise. What if you're working with smaller data sets and you cannot augment them, or you don't have all that data to train these models? These models will overfit, so that might not be your best option. And so do these techniques shared by these papers translate to smaller data sets? Are we as a community overfitting to large data sets, meaning that we are only looking at large data sets and perhaps not improving performance with smaller data sets? I'm not saying that that's the case, but we should ask these questions themselves. And does it make sense to work with small data sets? Yes, yes, we think so, because many applications rely on hard to obtain data. Because there are some regulatory issues even in big companies. Sometimes one division cannot access data that other divisions have access to. In natural resources, we have large amounts of data, but they are relatively smaller samples, so we can't really generalize that much without being clever. And also in medical imaging, due to of the issues with personal identification and building large data sets to train models. Some might argue that deep learning being data hungry, so it needs large data, and also that smaller models that work with small data should be fast, right? Well, not necessarily, because models still can be quite complex, and the training time is going to depend on the complexity of the model. Let's investigate one such model, and this model I'm going to talk about. It uses the LUNA dataset. LUNA stands for lung nodule analysis, and it is a dataset that has 188 annotated computed tomography scans, and it has non-nodules and nodules classified with their coordinates. This classification was performed by 4 experts in the field, and nodules are only marked as such if 3 or more experts agree that these are nodules. Well, this model I'm going to discuss, it takes a whole week to train a single GPU. So the single processing version takes quite a while to train. And why this model specifically? This model, it tries to learn the distribution of the nodules so that we can augment this data set and train bigger networks, because 3D convolutional neural networks provide state-of-the-art results, but they need large amounts of data. So the data in the data set is not enough, and we can augment it with this technique. So this model itself, it relies on an autoencoder architecture, which looks something like this. This is a fully connected one. Ours is a convolutional one, but for our purposes, this doesn't matter much. Well, what does an autoencoder do? It tries to mimic its input. So we pass something to it. It tries to learn some code, and from this code, then it tries to decode it and approximate its input. Meanwhile, while we're doing this, we may understand that we're trying to learn the latent features of this input data in a smaller dimension space. And assuming that we can learn the parameters of the distribution that we assume generated this data, now we can have a generative model. And once we learn the parameters of these distribution, we can actually sample from it and generate new output data. And by the way, we train these networks exactly the same way we train regular ones, which is by mini-batch or stochastic gradient descent. So we update the weights iteratively, sampling entries from a mini-batch. We compute a loss function, which is a cost function, and the derivatives for each layer, and then we try to reduce the loss, and so we take a step towards some scaling factor and the derivative of the loss. As an example, here we have stochastic gradient descent, which is mini-batch gradient descent with the batch size equal to 1, and we have only one parameter, and we have a quite smooth loss function. This is obviously an ideal situation. This doesn't happen in practice. But anyway, so if we have a weight here in the w-axis that generates this loss, we can compute its derivative relative to the loss function, and in this case it's going to be this. And now we can take a step towards this derivative, so we scale it by the learning rate, and now we have a new weight and a new iteration of the algorithm begins. And now, so the new weight is here, the loss is this one. We can now take another derivative, and once again take another step and have a new weight, and so on and so forth. In this case, this model is going to nicely to converge to the minimum, which is around here. Okay, so that's the gist of it, except that instead of one dimension, we have millions of dimensions in the weights. Also, we not only use one sample, but we use more than one sample, which again is mini-batch gradient descent. And so we take the mean of the proposed updates to the weights. So in here, we only had one direction, one vector. In mini-batch gradient descent, we're going to have many vectors, so we take the mean of those vectors and go in that way. And by the way, this process, the process of estimating the loss and computing the derivatives, it is easily parallelizable because the samples themselves are assumed to be IID, and so there's no dependency between the data. But we still have to either synchronize or have a synchronizing primitive to update the weights in all workers. So just another representation. In this case, we have one worker with a model. The model is initialized with some set of weights, and in each iteration, it takes a slice of the data, which is this block here, and it takes the data, computes the loss, updates its weights, and now takes another slice of the data, and so on and so forth until our budget expires or the model converts or fails to improve. We can actually do this, parallelize this by, for example, splitting the batch between workers. So in this case, the first mini batch goes to the first worker, the second mini batch goes to the second worker, and they compute their updates independently. Then we compute with an all-reduce mean operation the average direction in which we want to go, update all the weights, and keep going. So in the second iteration, the first model would receive the third mini batch, the second model would receive the fourth mini batch, and so on until convergence or the budget expires. Obviously, this only works if the models start with the same set of weights, so we initialize all the models with the same set of weights. So we need a broadcast as well. Most importantly, how we split our work is of utmost importance. So this is one way of splitting the work. This is not the way we perform it. We take the first mini batch, we would take the first mini batch in this case and give a half to this worker and half to this worker. So many papers and frameworks suggest that we increase the learning rate by k whenever batch size is increased by k. What we know is optimization will take a different path in the loss landscape. And the only possibility to have the same path is when k learning rate, when the learning rate is scaled by k. So this would be the update, the proposed update, in which the learning rate becomes this parameter here. But we can still think of the learning rate as just a single parameter, so let's call it alpha. And this is the update that we perform on each iteration. We go through each worker here and through each sample in the mini batch, compute the losses, take the mean, scale it, and update the weights. Well, obviously changing alpha directs optimization, and when we have alpha equals to k learning rate, we have the linear scaling rule, which is what Horvath framework for parallelizing models suggests you to do. This is from the MNIST example. So it's scaling the original learning rate by the number of GPUs. When alpha tends to kn being increased on each iteration, this is what we call the linear scaling rule with warm-up. And so again, Horvath supports this as well. It has this nice class that implements warm-up for us. So in this case, this model is increasing the learning rate until k original learning rate over 5 epochs. But what we do is we keep the batch size fixed, and we keep the learning rate the same. So if we have 2 workers, each worker will get half the size of the original mini batch. And if we have 3, each one gets 1/3, and so on. This obviously limits us to the number of parallel workers to the size of the mini batch. And communication is going to cost more relatively to computation, but this gives us the same convergence properties of the single worker case. So we know if the single worker case converges, our model will converge in parallel. And well, our models run faster than the single worker version simply because we are still splitting work. So our approach is strong scaling because work per iteration doesn't change. The work each worker does is divided. And the approaches in the literature are weak scaling approaches in which each worker performs the same amount of work. So in each iteration, as you increase the number of workers, data processed increases as well. So the methodology to compare all these approaches, which are the strong scaling, weak scaling without any scaling rules, weak scaling with the linear scaling rule and warm-up, was to train the same generative network with 1 to 32 workers because the original implementation used a mini batch size of 32 in this dataset I've discussed before. And we trained it until it reached a given loss, which in this case is the mean squared log error. Why measure the time to loss? Because since each strategy, parallelization strategy, uses different mini batch sizes, we know that reaching a given loss actually measures how much the model itself is learning. So this is the right thing to do here. The results then is that, well, strong scaling is the only approach that keeps improving and that converges in all experiments. Weak scaling does converge in all experiments, but it gets worse up to a point, probably due to some noise between communication, not only communication, but splitting the work, and so the directions of the computed vectors updates are probably noisier. The linear scaling rule didn't converge at all. It only converged in the single GPU case, which is equal to all implementations. And warm-up actually helped linear scaling, but it failed to converge from 8 GPUs on. Not only that, but if we take a look at the losses themselves, it's hard to argue for improving the number of GPUs. As we can see, times are a little bit confusing. And for strong scaling, we see that in each, as we add GPUs, the losses go down and the time gets way smaller. And as we can see here, the difference between these GPUs 8, 16, and 32, it starts to get smaller because communication starts to cost more. And what we see as well is that there's a huge drop in loss in the beginning, and this is due to the model learning the general characteristics of the distributions we are trying to model quite early on. So, for example, in 128 iterations, the model is learning something that starts to resemble the input distribution. You can see that in the 2D case, it's starting to mimic some numbers, and it starts to recognize the general look of some nodules, but it takes quite a long while actually to minimize the loss. And so most of the time is spent in the fine-tuning of these characteristics, and that's what consumes a lot of time. And parallelizing this model made us go from 1 week to less than a day training time, which is excellent, actually. So the conclusions are that it seems that insights obtained in large datasets do not necessarily translate to smaller ones. Models with modest data still can take a long time to train, as we saw. Strong scaling, in this case, outperforms in every metric weak scaling. And we expect these findings to generalize to other applications, but more experimentation is needed. Well, thank you for your attention. If you have any questions, I think you have to use the comments form, or you can just find me in one of these social networks.